Good afternoon. I'm going to talk about some work that's been ongoing in bits and bobs for a few years now, so I apologise we've seen some of this before. Basically, this is about doing really high fidelity tidal modelling, looking at modelling non-hydrostatic flow in extremely high resolution and using high fidelity tidal models for it. So this is a continuation of an ERC funded project which is Flowback, and it's now continuing under what's called the ECSC programme. I have support from Scottish Power and SAMS up in Oban. So what I've been looking at is the Sound of Islay, which is a proposed site for a tidal array by Scottish Power. This model is about 20 kilometres across and about 36 kilometres north to south, and it has a peak ebb flood current speed of about 3 metres a second. It's quite an interesting site because you have a lot of variety in the scales of the flow, from less than 25 metres to features that are 500 metres and more across. This is still a work in progress, so there will be some results, but I'm still downloading them from Oban, so perhaps next year. So, current modelling strategies. We have shallow water models like Telemac. These are very cheap to run, and they have a hydrostatic assumption. You have sigma layer models like you have Del 3D, you have FVCOM. These are kind of quasi-3D. Now, what I mean by quasi-3D is you have layers of essentially 2D flow with friction coefficients separating the layers, and these affect momentum transport from the layers, but they are hydrostatic. Now you have the fully 900 hydrostatic models. There's not many of these about, and you need this three-dimensional to capture vertical momentum transport, but it's extremely expensive. Turbulence metals that you have a constant eddy viscosity, where you add a viscosity to the molecular viscosity, which then accounts for the mixing due to turbulence. You have Reynolds average Navier-Stokes, and you have large eddy simulation, which is extremely expensive and is grid resolution dependent. So I decided to go for LAS or large eddy simulation, and like I said, it's extremely expensive to run, so you keep talking 80 to 500 computational cores running for about a month or two, which is extremely expensive. Like I said, it needs very fine grids. This produces masses of data, so I'm slowly downloading about 3 terabytes of data from Oban, and it's taken a couple of weeks, and it'll probably take another couple of weeks before I get it all. Most LS models, they parameterize what we call the isotropic turbulence. So that's when it gets down to the scale where the turbulence is no longer anisotropic, but isotropic, so it's relatively direction independent. This is a huge difficulty that I had to overcome. It's also, boundary layers are hard to model within LAS. The reasons for it is you can get a time series of data out from the velocity. You can get lots of detail out about the transient nature of flow within tidal straits. This can give you generate turbulence spectra, which you can then compare with ADCP measurements, and this I can hope will eventually lead to realistic tidal turbine interaction and fluctuating flow. That's a reference to my wind farm paper, which used LAS but for atmospheric simulation with a wind farm. And of course, this will allow me to resolve very transient features such as vertical flow, so upwellings and boils. And this is the Grey Dogs tidal race, which is just north of Scarborough. And you can see that's extremely non-hydrostatic. And a sigma layer model will just not be able to resolve that at all. So I needed to do some model development, and this is why it's taking so long. So I actually had to develop an anisotropic large eddy simulation model. It's very clear when you look at the flow in tidal straits that you're dealing with turbulence operating at different scales. You can see eddies that might be 500, 100 metres across. We also know that there's vertical structures that are perhaps only meters across. So you need to be able to deal with these separately. So I basically developed this model where I had separate eddy viscosities for horizontal and vertical components. I also had to deal with the boundary layers, so I used a thing called Van Dries stamping, which calculates the distance to the wall and then modifies the eddy viscosity. And I used fluidity, which gave me this non-dissipative finite element discontinuous Galerkin method. So it was extremely non-trivial to develop because I had to heavily modify fluidity to give me what I wanted. And there still needs to be so much work in terms of optimization. So 1 month of simulation time equates to about 3 months of runtime, which is, quite a lot. So this is the model running. If I can get this to work, there we go. So, I'm just pumping in M2 and S2 tidal constituents and ramping this up over 48 hours. So each frame here equates to about 5 minutes, and that's 12 frames a second. So, but what you can see is that eddies and recirculation are occurring around things like that promontory, which you can see on the west coast of Jura. Now, as we zoom in here to the strait itself, you can see where I think these are effectively a driven cavity, when the tidal flow essentially traps circulation with the into the coastline. Now, this is what happens is these coastal eddies seem to detach periodically, and this creates turbulence that's advected downstream. So this could have interesting consequences for putting tidal turbines in certain parts of a tidal strait. Now, with this model, when it comes around in a sec, well, you can see this is one of these extremely large tidal turbulence features. That's an eddy dipole, and the southward dipole is about 5 kilometres across. Now, what this has done here, this is now cut away into the model and showing a 3D cutaway of the velocity. So the thing this could be used for is perhaps providing boundary conditions to much smaller tidal farm models. Now, I should say the vertical scale is exaggerated by about 10, but what you can see is it's extremely complex flow, it's non-hydrostatic, it's mostly bidirectional, but there's a significant amount of variation. And what I've added here is I've added the bed stress now, so this can be for later work where we can look at sediment transport. Fluidity does sediment transport, so we can put this in. What I find interesting about this is you can see that there's the fluctuations in the flow, and perhaps some of those eddies are actually affecting the sort of bed stress quite significantly. And you can look at put the surface vorticity on top, and you can see the correlation between the two. So it's quite interesting. I mean, I haven't done a lot of analysis on this yet. I know the model works. I'm now, like I said, still downloading this massive amount of data. So there's still more to come. So results I do have. Managed to download one of the virtual ADCP sites. Scottish Power provided with 2 ADCP sets of data, and the model generates these with about 10-second sampling. So the graph on the top left is the flow speed near the surface, the ADCP1, and we can see there's some variation. There's not as much variation if I put in 4 tidal constituents. Now that would mean I'd have to run the model for 2 or 3 months, which would mean I'd still be waiting for them. The flow direction, as you can see, is relatively bidirectional, but there are some significant variations which occur over the tidal cycle. And on the right, you can see the velocity profile. Now, this is roughly a 7th power law. Compares quite well to ADCB data, but which I can't quite show you yet. Interesting thing about this site is the ADCB2 site looks quite different in the measured ADCP. It looks pretty much like a very tight log profile and not a 1/7 profile, whereas the other one is pretty much, as you can see, pretty much looks like this. So my to-do list, I need to do some turbulent intensity measurements, compare this with the measured data, get the second ADCP site out, and I'm also looking at the max velocity profiles, tidal gauge data, and I want to look at the flow rate of the flux. So I want to see how much is the net flow in one direction or the other, or is it equal? I need to do some more optimization, and fluidity needs a lot of work so it's easier to use for physical oceanographers. I've shown fluidity to some physical oceanographers, and it's far too complex in terms of the discretization. So I'm working together with some oceanographers to do that. And of course, because fluidity is open source, these improvements will be released back to the community as open source through the fluidity distribution. So in conclusion, large eddy simulations, they're really difficult. I'm hoping in 5-10 years' time I can just run this on a desktop and it takes 5 minutes. It doesn't at the moment. It does offer a prospect of great understanding of tidal turbulence, because we get lots of information out about the size of eddies, the frequency of their occurrence, the vertical structure, and we got lots of transient data out of it. Much work still needs to be done on developing new methodologies. I based my anisotropic LES, I did a search for LES and tidal simulations, and I found 5 papers. There's not many out there, so there's a lot of work needs to be done. And of course, the final thing, if I can get the fluidity to optimize so it runs 2 or 3 times faster, then I can resolve finer resolution turbulent structure and get even more out of the model. That's not too far away. I've already got speed up of about a factor of 2, so I reckon about a factor of 4 or 5 is quite possible. And that's the end of my talk.
This production is brought to you by the University of Edinburgh.